We're going to make it through the first day. So I'm going to give a talk here about customer support and IO applications at Liverpool. And some of the topics in my conversation today, I'm going to introduce our users and applications and give a somewhat chronological discussion of Luster at the Liverpool Lab. Talk about some of the events and aspects of Luster which have impacted the usability. A few things about our support strategies, and conclude with our latest and greatest success story on the IO side. So my role in the Luster project is sort of twofold. And one is to act as sort of a proxy for our end user community back to our local Luster project and to CFS and Sun. And the other role is basically as a use consultant to the end users. Just a little background. The nature of our applications, it's multidisciplinary scientific and engineering research. So we've got big 3D nonlinear simulations. And we have both scientists and computer scientists on our code teams. And so that adds some complexity in the support. We have a whole bunch of different platforms, but since our center really is in support of the ASC program, the current generation of the ASC system is called Purple, and it's IBM proprietary AIX, about 100 teraflops. And it's actually, we're a really big GPFS customer, so we got 100 gigabytes per second GPFS file system on that system. We have a lot of Linux clusters, and our whole strategy with the Linux clusters started in the ballpark of 7 years ago. The idea there is, how can we replicate the ASCII programming model and the platform architecture with all commodity hardware and software? And so for us, that was the beginnings of working on Luster. At the time, actually, I don't recall, there were 4 technologies that really weren't available to the extent we needed them to replicate an ASCII style of Luster. The file system and the interconnect were the 2 big ones at the time. Now, subsequently, we have this monsters BGL system, and now it's got 212 992 CPUs, and it's got 1 IO node for 64 compute nodes or 128 processors. So we have on that system 1,664 Luster nodes. A little different perspective on what our applications look like. So all our clusters are, at this time, we have a lot of nodes of modest scale, and this is on the Linux side. Individual jobs are running on hundreds to thousands of processes. Everything is coordinated by MPI, and perhaps there's some shared memory communication within the node. All the nodes mount a parallel file system, and all nodes could be writing to the same file at the same time, or every process could be writing individual file. And the codes are in C, C++, Fortran. One thing we noted a while back was that the writes to the file system dominate reads by about 5 to 1. And actually, interestingly, that ratio is changing. And the reason it's changing is relates to now we do read the data to write it to archive, and then often it's read back to Luster. And so once we got to the point where our parallel file system could be filled up, that ratio changed a little bit. So I said we were a GPFS customer, and actually we were one of the very first GPFS sites. And prior to having Luster in production, we had GPFS in production for close to 5 years, and that put certain expectations on how a parallel file system would perform. There was a real different sort of support required. That file system was totally, I mean, when it got to our site, we tested it and then gave it the thumbs up to go into production. So actually the team involved in supporting GPFS was actually almost exclusively on the application software side and not on the system software side. One of the things coming out of ASCII is one of the measures of how much bandwidth you need in a parallel file system is that you should be able to dump half of memory in 5 minutes. So as the half of the whole cluster. So as the cluster gets bigger, so does the file system. And actually another interesting thing in the early days for us for parallel file systems, we were advocating a lot different approach to writing I/O in the application. And it was basically we were strongly advocating using MPI I/O and parallel HDF5. And we had our sort of hand presentation on, here's how we envision the ASCII application I/O architecture. So in the project I was in at the time, our task was supporting MPI I/O and HDF5. And initially, through that time, the first version of IOR and subsequently the second version of IOR was developed. So our first Linux clusters, we did not have a parallel file system yet, but we still had some pretty serious I/O requirements. And so right off the bat, we had 64 NFS file systems that it was incumbent on the application programmer to figure out how to strike their data across those. Interestingly, one of the code, and I'll talk more about DDCMD, but that's going to be our success story. At that point in time, that they wanted to, after about every 2 minutes of simulation time, write several small files from each of the components. So for them, that was great, because actually 64 NFS file systems, you do have a higher aggregate file creation rate. That's a nice thing. And you also handle very small transfers. So we've got these Linux clusters, we've got the Luster project rolling, and we've got our management breathing fire down our backs to get Luster into production. And now this was starting months after the path forward collaboration between GPFS and Tri Labs. So we did get it into production, and once we got it into production, the whole support strategy for the customers changed dramatically. So the one-size-fits-all ASCII architecture was out the window, and it was like individual code teams that were having showstoppers. So, I mean, some performance problem, some data integrity problem, and there were some. When the code was, when Luster was really under a year old. Our support strategy evolved to like one-on-one remedial sort of assistance to the code teams. So we tried to document better practices, and occasionally the code teams took our advice. Another interesting thing, that probably most interesting to me at the time, was that I developed a survey for all the code teams, and it just to probe them on, you do a shared file process, how big are your files, how many files you write at each time step, how frequent are your time steps, that sort of thing. And it was a real eye-opener for me how different the usage was than what we had been promoting. And actually, another great thing about it was it allowed me to get to know the code teams individually. As Mark talked a little bit about earlier, initially we had a dedicated file system for each cluster. And at that time, the Luster team was mostly involved in fighting fires. So this, now I'm thinking we're about a year into production, and some of the customer frustrations are that the Luster robustness wasn't close to what GPFS was, and today that gap is pretty small. Our code teams are still not comfortable with the possibility that they'll hit a short read or short write, and that's an acceptable behavior under POSIX, that they ought to be checking their return codes and doing their own error recovery for that situation. And GPFS has basically its striping is automatic and dependent upon the file size, whereas with Luster, you have to manually, I call it manually, you have to determine the striping characteristics prior to, and state that, you can tell them about it. If it gets into their run scripts, it's probably going to move forward, but they're not going to remember it the next time they need to set the file striping. So what's going to happen is, hey, how come my performance went down? So that's a sort of a recurrent annoyance for us. So BGL, the monster, this would have been, I think we've added new hardware, it has its own unique and bizarre architecture. Mark talked about having a cluster just for data offload. Um, and pretty much at the BTL scale, all the middleware is broken. None of it works. In fact, I would say, like, my experiences with those three libraries is they probably were tuned at the level of 100 finds, and not a whole lot of, so almost, more than 5 years, there was no tuning with regard to scaling characteristics. And the thing about BTL, some of these customers, they still want creating a file more per process. So now, at that point in time, it could be 132 paying processes and 128 different. So the DBCMD team, at the time, if you recall, they wanted to do a simulation and then write a couple of files from every process. Well, it's actually their initial runs on DGL, the file creations was the bottleneck of their entire process. So for 2 minutes of simulation, they had more than 2 minutes of file creation to do that. And so we had another meeting with them, and what came out of that was sharing files at a lower scale. Now, by sharing, you can share files in a couple of ways. You could have multiple processes opening and accessing the file, but that actually doesn't solve your metadata problem. So here what I mean by sharing files is there's an aggregation step by communication prior to writing this smaller number of files. So moving forward to, say, a year ago when we were pretty far down the road with multi-cluster file systems. One of the things is, in the big picture, we have not yet achieved acceptable stability for the customers, but we were moving forward to the multi-cluster file systems. And we're adding a new series of our Peloton clusters, 6 new, bigger, better clusters to our existing 4, and adding more storage. At that time, at first we had 3 file systems on each network, and now we're at 2. So we saw a new wave of problems to support, and I would say many were contention related. BTL, actually, and it can still do it. I mean, you can basically wipe out, you can so overwhelm even the big file systems that we have attached to it that no other clusters have real access. And the other thing that's a little more subtle, now it's difficult to identify and localize the source of a performance problem. So when BTL had its own personal file system, the way we run it, I mean, when that file system was having a problem, we could go down a short list of codes that we're running on it, and it might just be one code, and identify the problem. Now we've sort of broadened the scope that we have to look. So I'm going to, before I go into talking about our big success story, I want to tell you about sort of this is when problems come to me that I can apply this approach. I'm really happy about it. One of the things, actually, and I wonder if other prior to working on IOs, I worked on more of the simulation side of HPC for about 10 years. And when I would talk to a code team and say, well, what does your code do and how does it perform? I really got some really good guidance as to their algorithms, their optimization, how efficient it was. Most of the time when I talk to a code team, sometimes, not always, they know what's going on, but often they'll say, oh yeah, I know everything about this IO application, does this, and this. We're not causing a problem. It isn't our code. But surprisingly, they really don't understand what their IO is doing often. And so one of the things I find incredibly valuable is to, backing up a bit, I mentioned it can be difficult to identify who's the problem child. We're getting a little bit of experience on how to do that manually. So say we can identify the code, and now what we'd like to do is just verify the problem, get a test case, or watch it with LMT while they're executing. And if that impact of that problem, if there's broad impact, we can ask them nicely not to run it anymore, or to tell us when they're running that. And so anyway, so next step is we found the bad guy, and what I like to do, I do a system trace and basically get all the traces, look at them. The kind of things I'm looking at are the file sizes, whether it's shared file or file per process. And looking at, you can merge the traces and see that there can be stalling. So it's, there's a wealth of information there. And so right now, for me, I prefer not to talk to them about what they think their IO is doing. I say, just give me a test case, let me profile it, let me talk to you about what I see. In a number of situations, we're able to map those conditions that we determined from the tracing onto our favorite test code IOR. And or sometimes we actually need to write a small kernel to try to reproduce that behavior. But often with IOR, and often we can then submit a Bugzilla with the R. A lot of times we have a lot of problem handing off a real application in many situations. So the general comments, and I think I've touched on all of these. One of the things, actually, when we've been able to identify that a customer was having a problem and go to them proactively, it was a huge challenge. And if you have any ideas on how we can improve that process of identifying and localizing the problem, that would be great. We have, at this point in time, we're not promoting the parallel IO middleware at all. And so I'm pleased to see some of that, the optimization efforts underway. And then I talked about my favorite way to analyze problems. So let's go on now to a team we've been working with for about 4 years. And I've mentioned them creating a heck of a lot of small files and post-processing nightmare. When we went to Luster, they saw this file creation bottleneck and modified their approach to do some aggregation of the data and thus have a smaller number of files to deal with. So actually probably June of last summer, Dave Richards and I were talking, and he had a question and a statement. And the question was, what can I do to my application to get the same performance you get when you do your maximum throughput runs? And just his comment, well, for the project we need a comprehensive life cycle plan for our data. So let's get into this a little bit. That gives a little background on what BDCMD is. And there's a lot of amazing things done with that code, but we'll just focus on the IO ones for right now. And what they're studying is called the Kelvin-Helmholtz with an L, two L's, instability. And this is a picture of a simulation, and you basically have two liquids and a shear force, and there's turbulence generated. One of the things actually, back up. One of the things about it, I actually had a background as a computational chemist. So one of the coolest things, this is really one of the coolest calculations in terms of the science it did, because it's an atomistic calculation that predicts a macroscopically observable physical process. So the turbulence is actually, macroscopic. So here's some of the notes that in this life cycle plan data. So you've got an initial estimate of the data requirements, and planning upon a restart interval in the range of 2 to 3 hours, and calculating out that their data rate is about 1.6 terabytes per hour. And so if they took a 3-hour restart interval and could achieve 10 gigabytes per second, then that would be 5% of their ballpark. And so that was what the target was. So when we started, it was writing at 2 gigabytes per second. And that wasn't going to be acceptable, and we'll see why later on that. But at the time, you'll recall, they were aggregating to about 100 files. And so they rescale things, so they're aggregating to 1,664 files, one file per IO node, and made sure, using mapping capability in DGL, that they were, you didn't land with 2 files on one IO node. They mapped it explicitly so there'd be 1 file associated with each IO node. Well, on the operational side, how are we going to achieve that? So there were a couple of suggestions. One was basically to dedicate a file system. And the second was that they could use both file systems and right in parallel to both of them. And so our answer was, and part of our considerations too, were how does the rest of the computer center stay in operation while they're doing this calculation? So one of the file systems was dedicated to the team, and we did not have them write to both file systems. They also, to conclude that data lifecycle strategy, they were planning on how to stream their data off to the archive. And using when they carried out that calculation, it was going to be fairly straightforward to get their data off. There was plenty of data to store. So it all worked. And actually, it worked better than we thought it would, because when they asked what was when they asked for our advice on what they could achieve in terms of throughput, we thought that there was no way they could exceed 10, and we were more comfortable with them for shooting for 6 gigabytes per second. But they actually were able to achieve 18 gigabytes per second. And so we don't know of a real application that does better. So there's a picture of the DVCMB team winning the Gordon Bell Award. And it was crucial to them to have that performance on their I/O so that they could have the aggregate throughput on that application. So I concluded here with the discussion of this heroic effort, but it wasn't only an I/O thing. There were similar heroic efforts on the algorithms, including some fault tolerance to hardware errors built into the application. And it was the biggest, probably the biggest single job in the aggregate for our archive system. And the visualization was also a huge effort. So from the Luster team perspective, we had a long working relationship with this code team, but in the end, we were caught trying to support our everyday requirements and these extreme requirements, and managed to pull it off. And so, in conclusion, I'll just say both from the Luster team and from our science team that we're looking forward to the next order of magnitude increase in peak IO. So that's the last one. So any questions?
How often does the system
Well, that depends on what you mean by grinding.
happy to leave more than this.
Let's see. Well, let me, say in this calendar year, we've had one code that has knocked us out a couple of times until we assembled our biggest system administrators and went and met with them in person.
He's not kidding, by the way.
will say it's you know, in the last 6 months, that's the only one I can think of. I mean, I can't remember.
They're running out of I know.
Oh, yeah, that one. But that's not grinding. But we've actually had another interesting problem that for customer support lately is that we've run out of iNodes on file systems. And it's almost, you know, I mean, these guys think they're unlimited, you know, so that was actually a particular challenge, determining who was the culprit and then cleaning that up.
That's also an user when saying virtual buses you have, it's just one
Right.
very, very stable.
Well, see, those users didn't do anything illegal. They didn't do anything illegal. It's unwise, but not illegal.
So besides the application of hefty system administrators, what do you think from a system software perspective would help ease any of the brittleness of the system that you have today?
You know, the one thing I think we've got in place a pretty good process once we identify users. So, I mean, maybe this sort of biases to making my life easier, but if it was easier to identify who was causing a problem, whether it was, you know, they consumed all the iNodes, or it was that they were assaulting the file system with, you know, 30 byte writes from BGL on every node. But, you know, identify that would be where I ask this. Well, let me answer the second question first. Yes, I do think it's worthwhile. And the reason I think it's worthwhile is, you know, at some, I mean, I think our code teams have been able to push, you know, some modification of the file for process, just, you know, make it good enough to succeed at the next scale. Most of them. You know, in the case of the application I talked about, they really they did all the things that those middleware layers did in a custom way for their application. That's always going to get the best performance. But there definitely are code teams without such extreme requirements that could, if those middleware layers were even reasonable at this scale, would provide them incredible convenience compared to